Second and a half lecture in this series on cognition and control in complex systems. And it's a great pleasure to have introduce my good friend and colleague, Ken Duffy, who we've worked together for quite a while. It was hard to get a bio from him. I really had to do some hunting. Just to say a few words. I mean, Ken is his PhD is in probability and queuing theory from Trinity College in Dublin. And he spent some time afterwards at a startup company called Corval, and he worked with Microsoft Cambridge. And reading his bio, you'd think he's mainly a communications network type. But at the same time, he did a lot of work both on applications and fundamentals of large deviations. And personally, he's been an incredible resource for ideas in statistics and simulation and large deviations. You might have missed on Monday his remarkable lecture on immunology, and basically, which is a beautiful control system, and his view on how to understand this. So he has an article that just came out in Science magazine on immunology. So Ken is quite a scholar in all areas of statistics and probability. And it's a great pleasure. It's a beautiful work here on decentralized constraint satisfaction.
Thank you very much, Sean. Thank you for the introduction. I think what Sean is trying to describe is that I'm very easily distracted by pretty problems. As a result of that, I've done work on all sorts of things. I'm going to talk today about work that I've been doing with Charles Bordenave, who's a very fine probabilist from the University of Toulouse, and Doug Leith, who's the director of the research institute where I work in Ireland. And Doug is a control engineer by background, but has been working in networking for the last 10 years. And before we get on to the body of the talk, I'm going to have two irrelevant asides. The first one is a gratuitous advertisement, which is that Queuing Systems is going to run a special issue on the mathematics of energy networks. And because I couldn't convince Sean to take over my role in it, I will be co-editing it. Thanks, Sean. And the last thing is, the second irrelevant aside is just that Sean and I actually do work together, even though I'm not going to talk about that work today. And this picture is significant for a couple of reasons. One is that Sean is smiling in it. Sean is smiling all the time, but when you take a photo of him, he always looks surly. And the reason he's smiling is he's pointing at my whiteboard at a formula we've just discovered. And the reason you can't see it is he posted this on Facebook and he cropped out the formula in case anybody stole it. But we're going to submit the paper this afternoon, so I can reinsert the formula onto my whiteboard. And this is related to the likelihood of unusual events in queues, which would be very distinct from the work that I'm going to talk about today. But anyway, on to the talk itself. So the basic outline of the talk, it's going to be leading from some practical problems to an abstraction and then back to the practical problems again. The outline is that we were motivated by studying distinct problems in wireless networks. And because most of them look quite apparently different from each other, the normal temptation would be to find solutions to each of them that's specific to the problem. But what I'm going to try and convince you today is that some of these apparently unrelated practical problems all have a single abstraction, a single framework within which they fit, and that if we can solve the problem in an abstract fashion, we can then specialize the solution back to the original practical problems. And the class of abstraction that's going to interest us is called constraint satisfaction problems, which are very old. You probably know about things like KSAT, which have been around for a very long time. But the interesting thing that our problems will have that weren't of the sort that motivated the original consideration of CSPs is that the variables in our problems will have a geographical location that means that the solutions, the way we're going to have to find solutions will have to be very strongly decentralized. Basically, variables or agents or whatever you like will be making decisions very locally, trying to solve a global problem. So it will turn out that although there are many beautiful and brilliant CSP solvers, they'll all fail our requirements of decentralization. So I'm going to introduce you to an algorithm that we've proposed. We're going to explain how it provably solves CSPs. I'm going to explain that the bound that we have on its performance, I'm not sure whether it's tight or not, so I'm going to actually try and give you a hint as to how the proof works, because we're not using any heavy machinery, and if anybody has any nice ideas about it, it's got to the stage where I just love a counterexample showing that our bound is actually tight, or someone to tell me that they know a piece of machinery where they can improve it. But anyway, the cornerstone of the whole talk and the thing that really motivates this as being distinct will be this issue of decentralization. Everything has this very strong notion of decentralization. Okay, so let's start with some motivating examples. And the first one I'm going to pick is how you schedule or how you organize access to a wireless resource. So let's talk about a Wi-Fi network. How do your computers all talk? How do they decide who speaks, who gets to grab the medium? Well, there's basically only two paradigms. The first of which we're using here today, which is to schedule the thing. So Marcy knows how long I have to speak for. So she allocates me a block of time, and then she allocates you a block of time to ask me questions towards the end. That centralized approach is good if you know what all of our demands are. You can use the time very efficiently. But of course, it's not very robust to inaccuracies in that information, or should the requirements change as time goes on. That's one point of view. The second point of view would be instead to play a random access game, which is much more like what we do in day-to-day conversation. Sean and I are talking while he's speaking. I listen and I wait till he finishes what he's saying, and then we somehow randomly interject to decide who gets to speak next. Both of these things are actually originally mandated in the 802.11 standard, but it's only the random access one is the only thing that you'll find in your wireless cards. The random access one has the advantage that because we're kind of playing a decentralized game, there's no central person who needs to dictate what's going on. It's robust to people coming and going, but there's a cost, or there's typically perceived to be a cost, and the cost is this, is if I speak and Sean acknowledges that he's heard it, and then I wait a random period of time, and in that time Sean decides he's going to speak, and I hear it, and I tell him I've heard it, and then at some stage in the future we may both speak simultaneously. We talk over each other, there's a collision, it's a waste of resources, and we have to adapt to it. And sort of simultaneously, two sets of guys, Jean Walrand and one of his students, and a bunch of guys from Barcelona said, well, why don't we have the best of both worlds? Why don't we have a decentralized game that finds us a schedule? So it finds us a collision-free schedule. The way it works in the Mac at the moment, the way the medium access controller works, is that every time we play the game, we kind of play it anew each time. So instead, let's see if we can find a schedule, but we're going to do so in a decentralized way. And the difficulty, or the decentralization in this problem, is how little information each transmitter in this system has. The information you basically have is that when you transmit, you can either, the receiver positively acknowledges receipt if everything has gone well. If they don't positively acknowledge receipt, all you know is that you've had a collision. You don't know whether it's been with one person or two person or who those other stations were. You just know whether you've been successful or not. So basically, each station, all it can measure is whether, so we're going to try and find a periodic schedule. So all you can do is you're trying to pick a slot in a periodic schedule. And when you've picked one, all you can tell is that slot free? Am I the only person using it? Or is at least one other person trying to transmit in that same slot? So you can imagine we can turn this into a graph coloring problem on a complete graph. And the way we do it is that we color the slots, right? So imagine we have slots colored. We're just going to, as opposed to numbering them, we're just going to color them. We're going to say that you could be transmitting in the green slot, the magenta slot, the blue slot, the cyan slot, and repeated. And each node here in this graph is then a station, okay? And the color of the node indicates which slot in this periodic schedule it has decided it will communicate in. And we have a complete graph because the links between vertices indicates that there's a constraint between them, right? And the constraint is green if it's satisfied. So here's what's happening is that this guy has picked the blue slot and this guy has picked the magenta slot. So they're happy with that. These two transmitters have both picked the blue slot, so they're unhappy. There's a clash. They're colliding. But the information available to each of these stations is they just know that currently the blue slot is not a good one to be transmitting in. They don't know how many other stations have transmitted in it, nor do they know any other information. Right? So they just have this very minimal amount of information. So that's our first problem. Second one, I'm going to get a lot of use out of this pentagon. The second problem, again, a distinct one motivated from wireless networks, will be this. And we started thinking about this back in 2006. We all use wireless networks. They're fantastic. They're free. They're cheap. They work relatively well. They all work either at around 2.4 gigahertz or around 5 gigahertz, one or the other. Most of them are 2.4 gigahertz. And if you switch on your wireless network at home and you're getting bad reception, one of the reasons might be that you have a neighbor who's picked the same channel as you. There's actually 11 channels you can pick from typically, depending on what country you're in. 3 of which would be non-overlapping if they were in the exact same space, right? So they're kind of slightly different slivers all around 2.4 gigahertz. And if you pick channel 1, 6, and 11, you can have them all in the same physical space and they won't interfere with each other. And the way most of wireless access points work at the moment is that they just have some default choice of channel when you switch them on. And if you've got a problem, you can go into the settings of your access point and change what channel you're on. But one of the things we're interested in doing is doing that in an automated way. And again, what sort of information? So if these things are access points, and what I'm drawing is a sort of interference graph between them, right? So there's a link between access points if, when they're on the same channel, they would interfere with each other. And again, I'm going to keep this structure of kind of a constraint between variables will be indicated to being unsatisfied if it's red and satisfied if it's green. But again, with the wireless access thing, part of the problem is that the range at which you can interfere is vastly greater than the range at which you can communicate. So again, the only information that's available to you is each access point knows when it picks a channel, it can measure the quality of the channel, and it can decide if none of its neighbors are on this channel, or if at least one is. Right? In some sense, there are occasions when you might be able to sniff packets and get extra side information, but in the extreme case, this is all you know. Okay? But the nice thing about this problem is that the reality is actually much more interesting than that. The reason wireless networks are so cheap is that they operate in unlicensed spectrum. And 2.4 gigahertz is around where your microwave oven works, for instance. So if you have your access point anywhere near your microwave, and you switch your microwave on, then that will destroy your channel in a very interesting way, actually. And it looks like periodic beacons because there's a period to do with rotation of the element within the microwave oven. So you have these non-network sources of noise, is the first thing. And the other thing is that we don't have a single adjacency graph. That's a falsehood of colleagues who have some nice measurements that show you, even though these channels are quite close together in spectrum, the propagation behavior can be quite different. So Sean and I might both pick channel 1 and interfere with each other, but we could both pick channel 2 and not see each other at all. Right? So the interference graph can change depending on the channel that you pick. Right? So it's going a little bit beyond graph coloring. We started with the Mac problem, which looked like graph coloring on a complete graph, and now we've got some funky form of graph coloring where we're trying to pick channels that don't overlap with each other. But we don't just have a single graph we're fretting about. And again, this is part of the motivation where we want to assume this most minimal information. We want to assume that the access point can basically tell whether it's satisfied on its current channel or unsatisfied. Because you don't know, one of the traditional views would be maybe access points would share information and Sean and I would agree to change channels. But if Sean's a microwave oven, I can't convince him to do something apart from, okay. So we have this kind of minimal information. And I wanted to give you one more example just to show you that this is really not all graph coloring, because I'm going to move quite far from graph coloring. But this is effectively motivated by a network coding problem that we're talking to Muriel Medard at MIT about. But I don't want to explain network coding because I'd be here all day. So instead I'm going to describe kind of, in terms of the abstraction, one of the difficulties. All of those previous problems I've shown you, right, those two problems, they're kind of like graph coloring, and that's a bit like agreeing to disagree. You know? Everybody is locally trying to make a decision that's distinct from their neighbors. If you're trying to do something that's a bit more end-to-end in a network, like set up routing paths or whatever, then it's much closer to consensus. And the reason for saying that is, okay, I could consider trying to solve a consensus problem with these decentralized constraints, which is something that a modification of something like this is what we're trying to do with network coding. And the reason for bringing it up is, one, it'll fit in this broader class of problems I'm going to worry about. And the second thing is basically it will reinforce something that you already know, which is that sometimes it's easier to agree to disagree than it is to form a consensus. So the decentralization here is what you're trying to do is everybody's trying to pick a single color that they will all agree on, but at any time, everybody only knows whether all of their neighbors are on the same color as them, or at least one isn't. Right? And that'll turn out to be a harder problem to solve in a very decentralized way, because with something like consensus, you kind of need a global view of the whole problem. Okay. So what is the abstraction? The abstraction that all of these things fall into are called constraint satisfaction problems. I'm trying to and explain them very briefly. If anybody has any questions, please just interrupt me. So the idea is that you have n variables. If you want to keep graph coloring in your mind, what you can think of is I have a variable for every vertex, and the variable dictates what color the vertex is on. So I have some finite domain of colors, and I have a finite collection of variables. And the abstraction of the constraints that we're placing on these variables are called clauses in general. And what they are is they're functions. So you give me an assignment of variables for the entire problem, and they're functions of those assignments, and they either return 0 or 1. And the idea is they return 1 if that assignment is currently, if that assignment satisfies that clause, and 0 otherwise. Okay? And what you're trying to do, and this is all about feasibility rather than optimality, is you're trying to find an assignment of variables so that every clause is simultaneously satisfied. Now, we're going to run through a few of the clauses corresponding to those previous problems I've been talking about. In general, these clauses could have any structure that you wish. But for instance, in the schedule finding, what is it? Well, we have n stations, so we have a variable for each station. We have a complete graph, so we have n choose 2 clauses, and a complete undirected graph. And if we have a schedule length of d, say, then what are the clauses? We'll have a clause for every pair of variables, and the clause will be satisfied so long as those 2 variables take a distinct value. Right? So it's a complete graph, so I'm neighbors with everybody, and I have a clause describing my relationship with each of those other people, and that clause will be satisfied so long as we're on distinct colors. In the channel allocation, maybe we have n access points. We have a number of graphs, right, because it could depend on the channel that we pick. And basically, as long as we pick orthogonal channels, will be satisfied. So I can write down clauses that depend not only on variables but also on their values. So basically, I'll be unsatisfied if Sean and I are neighbors on a given channel. We've both picked that channel, then I'll be unsatisfied, and otherwise I'll be happy. And with the consensus, it's kind of the reverse. In the consensus, you give me a graph, and the clause will be every pair of variables that are neighbors, they'll be satisfied so long as they're on the same, they've picked the same value, and they'll be unsatisfied otherwise. Okay. So this is just self-evidently saying that all the problems that we've looked at already are all just constraint satisfaction problems. All of these clauses only depend explicitly on two variable values, but that's not a requirement in general, of course, and you can do much more complex things. But what it's not capturing is this decentralization requirement that we have. So in order to capture the decentralization, what I'm going to do is I'm going to rewrite the condition for finding a solution in a completely trivial way by adding redundancies. What I'm going to say is I'm going to look at a variable-centric view, if you like. So for each variable I, if you let script mi be the collection of clauses it participates in, okay? So I participate in a clause if I can influence that clause's satisfaction or not, if I can influence whether it's 1 or 0. For instance, in the graph coloring, I can influence every clause where I am a neighbor on that link, right? And I can't influence clauses that have nothing to do with me. Well, I'm going to rewrite this, and as opposed to saying that we're looking for a solution where every clause is simultaneously satisfied, forget this outer min I. For each variable, what this is saying is for variable I, this is 1 if variable I is satisfied. Namely, if every clause that variable I is involved in is currently satisfied. So what we're doing is we're looking for an assignment so that every variable is simultaneously satisfied rather than every clause is simultaneously satisfied. And the reason for doing that is the decentralization is basically telling me that this inner thing is the information that's available to variable I. So what are we trying to do? Okay, we're trying to find an algorithm. First thing is it better be a solver. So it better solve these problems if they're solvable. So we'll let time be discrete and we'll let the algorithm evolve in time. So for sufficiently large time, sure, certainly. No, yeah, very good. So I'm going to get onto that in the next slide, but I'm going to, no, I'm going to answer it right now. It's a great question. So the idea is that you'll just be able to, that will be returned to you. Let me tell you how. Imagine I'm an access point and I've picked a channel. Right. So I don't know what everybody else's assignment is, but I use the channel and I go, is this working for me or not? Right, so you're right. So I don't know what clauses are out there. I don't know the variable values of anybody else, but I can tell if I'm satisfied or not. I'm usually not satisfied. But, okay. Yeah, right, that is, as you say, a whole, that we'll have to solve offline. Okay, but you're absolutely right. That's what I'm going to, my constraint is going to be that I don't know the clauses, I don't know the variable values. All I know is whether my variable is satisfied or not. So that's what I'm being told. Yeah. So the first thing is just to be a solver, for any algorithm to be a solver, it better ultimately be the case that if there is a solution, I should find it. Okay? The second thing is because I dislike simulated annealing. What I'm going to say is that if you give me a solver, the first time it finds a solution, it should stick with it, right? Because I don't like algorithms that find solutions and then don't recognize it. All right. But the decentralization, which is what we're just being asked, is the decentralization. Each variable is basically going to pick what value should I have in the next iteration of this attempt to find a solution, in the next iteration of this algorithm, based solely on the information about whether I'm presently satisfied or not. And in particular, what you don't know is I don't know explicitly the variable value that anybody else has chosen. I don't actually know the participation sets. I don't know what clauses I'm involved in explicitly. I don't know what clauses anybody else is involved in explicitly. And I may not even know the functions that define the clauses, because whether Sean is an access point and is himself adapting or not, or whether he's a microwave oven and is not adapting, I just don't know. Right? I don't know what the sources of noise are, for instance, in that problem. So all you can tell is the kind of cumulative effect of all of these things, which is basically, am I presently satisfied or not? So if it was for instance, the choosing the channel problem, what it is you select a channel. As a network, you communicate on it for a while, and you look to see, is there much noise on it? If the noise threshold is, if there's not a lot of noise on it, you're satisfied, and otherwise you're not, That's the kind of idea. And as I said, this is very strongly motivated by the sort of problems that we were worried about, and it's not the sort of things that people normally worry about when it comes to CSPs. I should say that there are some very, very beautiful and elegant solutions to constraint satisfaction problems. All of them are very centralized. There's a big competition run every year, SAT race, where people can solve problems with like 10 million variables. Very impressive stuff. They're usually based on one of three ideas. There's one that goes back to the 1960s, DPLL, and that's a very deterministic way of solving the problem. You give me the whole problem. I assign everybody a single variable value, and then what I do is I do an entire search of the whole possible space by changing values of certain variables repeatedly until I get more and more satisfaction, and I kind of build a tree. I dive down, changing and changing and changing. If eventually I can't change those variables anymore and find a solution, I retrace my steps to the last place where I had a branching point and I could do something different, and I search that part of the space. I have to know the current assignment of every variable. I have to know the whole problem, but it works very well, and because it's deterministic, it can be stochastic in how it does its searching, but it's never going to ask the same question twice. It's never going to assign the same variable values twice. You'll see, of course, we're going to assign the same variable values twice. There are ideas based on gossiping, which is the sort of thing that Sean will be an expert on, where you locally garner information and you try and spread that through the network, some sort of control signal. But again, to do that kind of thing, you usually need to be able to share variable values between neighbors, which we're not allowing you to do. And then the last one, which I'll mention briefly, and again, these are just the sort of approaches that people take, is called stochastic local search, which is, again, quite a pretty idea, but very centralized. And what you do is you uniformly pick an assignment of variable values, and then you look how many clauses are broken. You pick one of those clauses uniformly at random. You pick a variable value inside that clause uniformly at random, and you toss it uniformly at random. And you see, does it improve things? And of course, you see, if you fix that clause without breaking any others, next time round, you'll be picking uniformly from a smaller class. And there's a general belief that can be made rigorous in certain senses that the solution space is relatively sparse. Solutions have a tendency to be quite far away from each other if you try and put a geometry on the space. And so what stochastic local search, the local in it, is I pick a point, a variable value x uniformly in the whole space, and if n is the number of variables, I take 3n steps trying to improve that original choice to a solution. And if I don't find a solution in 3n steps, I just reset, pick uniformly at random again. So it's like a separation of timescales in the dynamics. I have something at a very high level, picking variable values very extremely, and then on picking a location, I look locally to see, is there a solution near there? But again, all of these things are very heavily centralized, mainly because they were never motivated by the sorts of problems we've been fretting about. So none of them work, and most of them, well, we couldn't see an easy way of converting them into something that had as little information as we have. So let me instead describe an algorithm that we've proposed and that we can say a little bit about. Just going to check on the time. Okay. So the idea is that each variable keeps a probability distribution. And the probability distribution in some ways records how confident it is that a color or a variable value is the value for it. So we're going to initialize it to be uniform, and then what you do is at each time we're going to pick our variable value from our own probability distribution. Right? And what I'm going to do then is I pick the value, and then I look to see, am I presently satisfied or not? Because that's the only information that's available to us. And if I am satisfied, so I've picked a color, or I've picked a variable value, and I'm presently satisfied with it, what I'm going to do is I'm going to stick with that value with certainty in the next round of the game. Right? And this is what's going to give us the global stickiness of the algorithm, because if we're all simultaneously satisfied we've found a happy color, we're all going to just stick with it. Right? So that'll give us the absorption, the thing that simulated annealing wouldn't have. The question is, what do I do if I'm unsatisfied? Right? So I've picked a variable value and I'm unsatisfied. In the simplest case, you could just pick uniformly. For the math, that would be the same as what I'm going to describe. And in fact, I'm not going to describe it in great detail. The rough idea is that if I'm unsatisfied, I want to kind of learn. So basically, Sean has been picking blue for a while, and that's worked very well for him. I'm still trying to find what kind of color suits me. If I bump into him, he shouldn't forget that blue really has been working well for him for a while. He should resist my attempts to make him dissatisfied. I think Sean usually resists my attempts to make him dissatisfied. So the way that works is you put a little bit of learning into it, right? So you have some sort of convex combination of your probability distribution that you had last time around with the probability distribution, with a uniform, basically. Something that discourages you. You know you've been unhappy picking this color, so it moves some probability mass off it and onto the neighbors. Right? But it can be parameterized and can give you some stickiness so that if you do find something that works for you, you have to be, external people have to dissatisfy you a few times before you'll move. Again, it's very important for the practical convergence of the algorithm. For proving anything about it, it's irrelevant. If you wanted, you could just pick uniformly. Very good. I hoped I wouldn't get asked that. The B is just the idea is, again, you want a convex combination of probability distributions. The B is just basically you're saying whatever distribution I had last time, I'm assigning it mass 1 minus B, and then the B that I've left over, I'm redistributing in a certain way. The original redistribution that we would have had would have just been I'd take that B and reassign it uniformly to everybody apart from the value that I've just had a clash on. Right? It's just a way of saying I'm discouraged because this value hasn't worked. I've put in an additional A for the reason that it makes the proof work an awful lot nicer. So the idea would be A will be smaller than B. A is a measure of your aversion. So it's your aversion to, the B is just a memory parameter, and the A is a measure of how adverse you are, how upset you are when you have a failure on a given color. Right, so it's your aversion to using that color again. Right, that's right. That's it. But, yeah. That's right. We stick with certainty when you have success. It's more. Yeah, yeah. Because what I'm going to describe, the only theoretical result I'm going to describe is one about the complexity. None of it will matter, is the honest fact for the complexity proof, because it's going to be a proof that works no matter what your problem is. And you can see that picking the B and the A if you want that finer detail of how you should pick it, it depends on the sort of problems you're solving. So, for instance, for random k-sat, if you pick B to be about 0.05, it seems to work really well. So what it's saying is basically if you're very resistant to moving off, so if you locally find solutions, then you don't want to be too easily perturbed from them. I'll show you an example in a minute, but the interpretation is exactly what you've described. It's basically, it tells me how I redistribute my likely happiness after I've been unsatisfied. Okay. And it has the property the way I've described it as well, that it means that if you consider the state vector of being everybody's probability distribution, then the underlying process is Markovian. Although it's a nasty Markov chain, I think Sean would agree. So the idea is everybody's doing this in parallel. And if we're all simultaneously satisfied, then what will happen is we'll all be picking with certainty the same color again as the future. So this is why we find a solution. It has other very nice and natural properties which you would never work into the math, I guess, but are relevant to the practical application, which is like if the problem changes, those nodes become dissatisfied, and if a global recoloring is necessary, it will propagate from them. So there's no coordinated restart. It's not like simulated annealing. There's no global temperature we all have to fret about because I don't want any global information. And what I'm going to try and do, I'm going to do two things. The first thing I'm going to put the cart before the horse and tell you the corollary to the theorem. The corollary to the theorem is that if you give me a solvable constraint satisfaction problem, then this algorithm will find a solution in almost surely finite time. So at least that's a sanity check. It is a solver. You give me a problem that's solvable and it will solve it. The reason I'm putting the cart before the horse is that, for one thing, the theorem looks a little ugly, but the theorem is basically, okay, give me some epsilon and 0, 1, then the number of iterations that the algorithm will take before finding a satisfying assignment. If you want to find a satisfying assignment with probability greater than 1 minus epsilon, is some ugly monster that depends on the parameterization, but let's not fret about that. The thing to fret about is I have an e to the n squared, right? Now, this is a complexity result because I said give me any CSP, right? I've not given a particular class. In general, CSPs are known to be NP hard, which means I don't expect to do better than e to the n, n being the number of vertices. But e to the n squared is a little bit on the harsh side, right? And the truth is, I don't know if this is loose or not. So I'm going to actually give you an indication how we get to the e to the n squared. And if somebody can give me a counterexample, so if you can construct a sequence of problems that are really hard, or if you can improve the bound, I'll owe you a pint of Guinness or something, which is currency in Ireland, in case anybody didn't know. What I can tell you is that if you restrict to just graph coloring, there's something distinct between graph coloring and a general CSP, and I can reduce it to order e to the n, which is all I can ever hope to do. It's NP hard. I can only have something that's order e to the n. So kind of the reason for telling you this is to say that there's some gap, at least in the method of proof, between graph coloring, or actually the consensus problems, and a general CSP. And really this gap appears. I'm going to give you an indication why. Okay. So now we're going to try something very unusual, which is I'm going to explain how this proof works by Java applet. Okay. Which I admit is not a standard technique, and you would probably fail people if they provided a Java applet in an exam. But I'm amongst friends, and I hope you'll let me away with it. This was a Java applet that a couple of interns wrote for me over the summer, who are great guys altogether. I just gave them a rough idea, and off they ran with it. It was super. Okay. Let me explain how the proof works. Right. The thing is, I'm not assuming any structure of the problem whatsoever. So therefore, I need to do something with an awful lot of uniformity. Something that says, no matter what state the problem is in, I want to construct a sequence of events that will lead me to a solution with a probability that I can lower bound. And the way the sequence of events will work is it will be in n steps. No matter how I start, in n steps, I will lower bound the probability that you find a solution. Okay? And the problem will be that for a general CSP, that probability will look like a probability to the power of n squared, and for graph coloring, it will look like a probability to the power of n. And of course, the whole point is this is a Markovian system, so that if I don't find a solution in those n steps, well, maybe I'll find them in the next n steps. And I get a geometric bound, and that's where all the complexity things come from. But I just want to explain the core of the idea. So here's a ridiculous sequence of events which would lead you to a solution. Right? So here we've got a graph which is 6 colorable. And again, retaining the structure from earlier on to help you see broken clauses. The broken clauses, we're trying to graph color. The broken clauses are in red. Okay? Green clauses are happy clauses. So we've started in some configuration where a handful of people are unhappy. How do we get from that to a solution? Well, this is one way that could happen. Not very likely, but it's possible. What could happen is we can spread dissatisfaction. Again, no sly remarks, Sean. We could spread dissatisfaction to everybody in the room, which is indeed perhaps what I'm doing. And the way you would do it is basically say Sean and I are colliding on blue and we're neighbors with somebody else behind him. Then we could ask the question, what's the likelihood that both of us pick the same color as the person behind them? And now they're dissatisfied. Now what's the likelihood all three of us pick a color of one of their neighbors? And so on and so forth. And we can spread the satisfaction so everybody in the entire problem is presently annoyed. And once we're all presently annoyed, we all just remarkably jump to the solution. Okay? Could happen. Not entirely likely, but it could happen. And the thing is basically, how many steps this takes to propagate across the entire network is of order n, because we basically pick up no fewer than one neighbor in each iteration of this growing annoyance. The problem is the number of times I have to control the decisions that we make is of order n squared, because this first person, I have to have made him pick n colors in a row. Someone in the middle, I'll have to have made him pick like n over 2 colors in a row. And so I sum up them, I get something that looks like n squared over 2. And this is why this, although it's a uniform, very uniform thing, in that it works no matter what, it's why it looks like quite a loose bound. But again, it works for the general CSP thing, not just for graph coloring. I'm going to stop it when it gets to this final round of iteration and explain why you can do something a little bit better if you knew it was actually coloring. Okay. So if it was coloring, I'll just leave it running in the background. If it was coloring, the nice thing is the structure of the problems means that you kind of have interiors and exteriors. So what I can do is I can spread dissatisfaction from a group of dissatisfied people, but as opposed to all of us having to stay frustrated the entire time until a solution is found, I can propagate the dissatisfaction from us. So what happens is me and Sean are annoyed, we annoy our neighbors, we annoy our neighbors' neighbors. Now after that, they can annoy their neighbors' neighbors, but me and Sean can pick the answer and we won't ever be troubled again. I basically put out this wavefront of dissatisfaction, which you can see propagating from here, basically saying once you're sufficiently far within the interior, I can set you as a value that you will never be perturbed from again. And the point is, in something like the coloring or the consensus, there is a notion of an interior, and in a general CSP, I have no idea. I don't think that there is an equivalent notion of an interior.
Why would it not come back?
Oh, because so this is you're defining a specific sequence of events that's possible, not one that you're saying the algorithm is particularly likely to take. It's just one that's possible. So we annoy you, you annoy him, you annoy him, but now me and Sean are, he's far enough away that him being annoyed doesn't trouble us anymore, so we jump to a solution. He's still close enough to you that he's annoying. He annoys the next person. It's just a possible sequence of events. And it's possible to create no matter uniformly over the current state of the network. We're either in a solution or someone is annoyed. If someone is annoyed, then there's a sequence of events that within n steps could potentially lead them to the answer. But you're totally right in the sense that this will give you a reasonable idea of the performance of the algorithm if this was how the algorithm found solutions. Right? So if either of these sequence of events I've described were the typical way that the algorithm solved problems, then I would get a good estimate of the performance. People are going to think we teed this up, by the way, where you're asking me questions just before I'm showing you something, right? People are going to presume that we've... Sorry? That's right. In principle, I'm saying nobody can communicate other than by a not. Sure. No. So the interference graph is described. Yeah. Yeah. I'm not doing it based on power, if that's what you mean. Yeah. 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 And in fact, I'm using this as a method to describe how the proof works. In general, you can have clauses, as I said, that depend on the channels that you pick, or you can have, yeah. I'm only trying to use it as a descriptor. But the thing is, yeah, okay. But these sequence of events would give a reasonable idea of the algorithm's performance if that was typically how solutions were found, right? And certainly that one where dissatisfaction propagates through the whole thing and that they remarkably jump to a solution doesn't seem very likely. So running the risk of running you a stochastic simulation, instead, let's see how the algorithm actually would solve a problem. Okay? So here's a graph that's 4-colorable. And each vertex is running the algorithm as standard. Red indicates that the two neighbors are on the same color and therefore they're dissatisfied. So let's just run it and let's see how it behaves. So this is actually how the algorithm solves problems. How it solves problems is locally people find a coloring quite quickly, right? So these people have all found a coloring, these have all found a coloring. And then what happens is dissatisfaction spreads on a boundary trying to patch those colorings together. Right? So it's like this part of the network has figured out something, back part of the network has figured out something, and then on the boundary you try and superglue them together. Yeah? I'm going to run that again, just to, at least to prove that this is a stochastic simulation and I'm not just making it up. So of course, once locally they found a recoloring that works, that is a solution, they stick indefinitely. Now the thing is, going back to the parameterization question, I've intentionally picked a very bad parameterization of the algorithm here so that we can see this happen. If I picked a decent parameterization for a problem of a similar complexity, then this is what it'll look like. My beta, how I'm learning. I'm learning in a really bad way in that previous example. Which again, the math can't really manage, or certainly not in complete broad generality. There is probably no universal B or A. But this is a better B. If I... Stochastic, Sean, don't read too much into it. But you can see what it's doing. It's basically we're finding local solutions and we're patching them together. It's just on the boundary that the satisfaction tries to reorient things. And that boon, the reason that that works so well and again, this is just, I'm trying to be frank and honest and explain where things are good and where things are bad. That while it's a boon for solving graph coloring, where we're all trying to agree to disagree, is a problem if I try consensus. So this is a consensus problem. So here what will happen is a link is dissatisfied if the neighbors are distinct colors, and they're satisfied if they're the same, right? And if I run it on this, you'll see the exact same sort of structure, in that locally people have decided green is good for us or blue is good for us, but there's no global picture. And how do you patch together blue and green? The only way you can do it is by annihilation. But the thing is, these blue people in the corner, they don't know that they're totally outnumbered. Right? There's no global information, no... This is still just an NP hard problem, and I still think the algorithm is just NP hard on it. But it is showing the feature of how the algorithms work. It's trying to do things very locally, and the way you get a global solution. But the problem is something like consensus, it really is a global property you're looking for. And that makes it a lot harder. Without some extra control information or whatever, which we personally want to avoid. But for instance, as I said, we're trying to use ideas such as these for something that looks a little like network coding. And there you really have kind of end-to-end links. And basically, the reason I hacked this up was to try and illustrate to collaborators what was going wrong. And what's going wrong is basically that. The very extreme localization is a problem for something that has to be end-to-end. Okay. Right. Just for the pictures, you mean? Oh, the... Oh, again, this, okay. Let me, nobody suffers from epilepsy, right? It's a serious question, sorry. No, okay, no, all right. There, for instance, is attempting to graph color on a star, which is very hard. These are all just for illustrations for the talk. I can explain in detail, if you'd like, how each of those simulations were generated. And in fact, the applet's available on the webpage if you want to go play with it. But they were only for illustration, so those graphs were intentionally made planar. And they were done so, they're random geometric graphs. And you can do so in a way that ensures that they're planar. I have an Erdős-Rényi random graph, I could show you it, but it just looks like a mess. And we have some other specialized ones. But again, it's only for the purposes of illustrating features of the algorithm. Trying to get graph color something like a star in a decentralized way is very tricky. It will work, but just to explain, even graph coloring can be hard because there's only two solutions. Everybody on the outside is blue and the inner guy is green, or everybody on the outside is green and the inner guy is blue. Let's see. Okay. But I can tell you in detail, if you'd like, how these things were generated. But they have no connection with each other. They only have a connection to the central node. Yeah. They're just kind of typical examples of things that are hard. If it was centralized, graph coloring this is very easy. You know, but it's kind of illustrate. It's all just done for the purposes of illustration. The proof works in generality, and not only that, but I'm not really gonna show you today. But those two ones I was emphasizing. Yeah. Right. Right. Yep.
Do you have any sense of how sensitive this thing would be to even small amounts of noise? So
Yep.
if I assume noise much less than sort of the inherent dynamics of the, would it keep going all the time?
I guess if you continually have noise, it probably would. I mean, so.
No, but the reason I'm asking is you're trying to converge towards this solution, and by the theorem you
Get there.
almost surely are going to get there.
Yeah.
But if there is noise, that almost surely could extend it indefinitely. And that's the intuition behind the question, but I don't know if it makes any sense.
Let me say two things, which may be tangential, and if they don't quite answer what you wanted, just no, that's okay. Okay.
Computation of the class is, yeah, that's an example of exogenous noise.
Well, let me. Sure, right, but well, yeah, okay. But so the thing is that one of the points is that feature where you're locally finding solutions. That was very desirable for what we were originally trying to do, which is to pick channel allocations in wireless networks. Because what it's saying is basically that lots of the network is working quite well. So even if there is a problem and the problem is propagating, it sort of does so locally. So relative to the entire network, most of your network is working well and bits of it are performing badly. The noise thing is kind of interesting because, as I was saying, this is about feasibility rather than optimality. And if you had a utility function on the solutions, right, that even when we find a solution, maybe you don't want to stick at it. You know, maybe you want to go see if there's a better solution. And people are interested in that in decentralized games and multi-arm band-up problems. And the issue there is you can't handle the sort of generality we're looking at because even characterizing the solution set is very hard with coloring, let alone anything else. So, and I can't tell you, if you look at the stopped measure, if I look at the empirical measure of the process when it finds solutions, I can't tell you anything about what that measure looks like. I have some possible solution set. It's definitely not going to be uniform. Some are going to be more attractive than others. And the reality is that the problems that originally motivated us, I'm not going to show this stuff, but one of the nice things about where I work is there's a big networking group, and as well as doing the more theoretical end of this networking, which is largely what I'm involved in, we do work it all the way through to hardware prototypes. So we have an access point that picks its channel in this way, and it has to discretize things anyway, right? Because when it picks a channel, it has to decide, is this okay or not? And that's a very yes/no decision based on more information, you know, based on some finer subtleties. But it works very well. Or you can parameterize things. Again, the general algorithm, I expect you'll have to localize it for specific problems. Okay, but we're near the end. I don't know how I'm doing for time. I'll just say I could have. I just can't show you plots of boxes and things. It just wouldn't be exciting. And we also have that MAC thing where it's sort of a substitute for 802.11, where you're trying to find a decentralized schedule. We also have an implementation of that on Broadcom cards, which are in every iPhone, which works really well. But just to say, very quick example, something like this, where you take the corner of 5th and 59th Street in downtown New York. Maybe I should have picked Gainesville, but I don't know if people have war driven here. There's like 81 access points in that neighborhood. And the question is, if you switch them all on instantaneously and they were running this algorithm, how long would it take them to find a solution? And for instance, here we have a notion of physical distance. Often these sort of things you should describe as T-coloring rather than coloring, so that you and I are very far away from each other. So maybe we can be on channel 1 and channel 2 and not interfere. Sean is closer to me, so maybe when we're on 1 and 2, we will interfere. So I can have these kind of different radiuses of distances, which is called T-coloring. And if we do something like that with reasonable parameterization, what we find, given we have a hardware implementation that takes about 10 seconds. It actually takes about 3 seconds, but let's say 10 seconds to decide whether a channel is okay or not, then this network would find a solution within something of order of 4 minutes. So you have a blackout, everything gets switched back on, and within about 4 minutes you found a solution. Nobody's annoying each other. And as I said, we do have real hardware demonstrations of this. So the conclusions, I'm sorry for running over a bit. Basically, the point was that these apparently disparate problems can be cast as constraint satisfaction problems. The key thing that makes our application difference to historic ones, which are all about compiler rather than just allocation and registry allocation and compilers and things, is that we have a geographic notion of the variables, and that necessitates some decentralization in our solver. So we have some solver that well, it provably converges, and it seems promising for the problems that we had in mind. It seems less promising for things like consensus. I don't know if the general bound is loose. It could be that I have to impose structure on the problem in order to prove anything tighter than that, but I really would like to know if it's E to the n or not. If anybody has any great ideas, love to hear them. We haven't spent any time, which would again be the standard mathematical thing, if not networking thing, of looking at very specific classes of problems, specific sorts of graphs. If you have a tree-like graph, I suspect it's polynomial time, for instance, the complexity rather than exponential time. A philosophical question for the information theorists in the audience is, can you quantify the cost of this decentralization? Because we're throwing away a lot of information. So I don't know if you can even think of a decent measure of the cost of decentralization. And then coming back to that, that last question, it really is about feasibility. And at the moment, we're sticking with the first solution we come across, but it may not be optimal. And I'll leave it at that. Sure. So on random KSAT, they're quite comparable, right? But it depends on the problems that you define. Seems to be DPLL is a little bit faster, but they're very similar, yeah. And it seems to outperform one of the popular stochastic local search. It seems to outperform it for whatever reason, which is a bit embarrassing for it, given we're using very little information. But on very big problems, it's hard to tell because they get hard very quick, and DPLL will find solutions, and nothing else will. So I don't know. Okay. Sure. CSPs. I'm not sure. I'm not sure is the honest answer. I think they are very closely related, all right. But again, I don't know what the decentralization would mean. Yeah, I think that. Yeah, I think that. I mean, that's why I think the problem class is novel. Is basically the geographic location of the variables. Without that, we're just doing the same thing as everybody else, and I wouldn't be doing it. Yeah. I don't know if Sean has a comment. Yeah. Right. And maybe if you look at the relaxations, you do a lot better or something. But I mean that's part of the appeal as well. As part of if you have a very decentralized algorithm, it also lends itself to decentralized computing. And that I know you're interested in cloud computing, right? But if you're running variants of the algorithm on various trying to solve a big problem in little pieces is kind of appealing. But I think, so what I was going to say is, if I gave you a consensus problem, a centralized algorithm will solve it like that, right? Because it will just say, I'll give everybody the same value. So the fact that we're comparable with DPLL on KSAT suggests to me that random KSAT is not sampling the space of all possible problems in a nice way. It doesn't seem to be picking problems that are hard for us.